Hello, and welcome to this webinar in the TOPIQ webinar series. This webinar is concerned with the collection of powder data from a single crystal instrument using only micrograms of powder. My name is CrysAlisᴾঈশ্বৰৰ, and I am accompanied by my co-host, who is called also CrysAlisᴾείμᵒ. The two of us are application scientists at Rigaku Europe SE, stationed in Neu-Isenburg near Frankfurt in Germany. This webinar is being recorded. The recording and the process data will be made available to you. You will receive an email with download instructions in the aftermath of this webinar. If at any point during the webinar you have a question, please feel free to submit it by clicking on the Q&A button on the bottom of the Zoom screen. My co-host will collect all questions and we will answer them by the end of the webinar. Before we start, I would like to ask all of our users to join the Rigaku X-ray forum. Here you can get updates on Rigaku activities, the latest version of CrysAlisᴾṕ, and interesting discussions on all fields of crystallography. If you are already a member of the forum, I would like to encourage you to submit your specific, to subscribe to your specific fields of interest, so you get email alerts when something new comes up. All data we discuss stem from a Rigaku XRD SynergyS system. We used the kappa source of a dual flex system with kappa and molybdenum photon jet sources. The radiation source is also equipped with the dynamic divergence control. As the detector, we used the HyPix 6000 HE hybrid photon counting detector. As sample, we use naproxen, an anti-inflammatory drug. Why and when should you use your single crystal diffractometer for powder diffraction? Sometimes single crystals are simply not available from your synthesis, or you already know the structure and want to control your synthesis outcome without performing a sometimes time-consuming crystallization. Under these circumstances, you want to perform a powder diffraction experiment. Powder diffraction is also a great tool for analyzing the composition of bulk samples or mixtures. You might also not have access to a powder diffractometer, or you only have micrograms of sample at hand. While for most powder diffractometers, at least milligrams of sample are required, only micrograms are needed on a single crystal diffractometer. Most single crystal instruments are already equipped with a temperature control device, like an Oxford CryoStream, while most powder instruments are not. That comes in handy, as you can easily employ these devices for temperature experiments. Furthermore, we can analyze even materials like fibers or polymers by performing a stress analysis or pole figure measurement on a single crystal instrument, while powder instruments need special attachments in order to do so. But today we will focus on the collection of powder data for quantitative analysis, and we will start with the sample preparation. Most sample preparations will be performed under the microscope, which will be present in most single crystal laboratories anyway. Here we can get a good estimation of the crystallite size. If the particles look like the one on the left-hand side, you should definitely perform a single crystal experiment with those crystallites. But if you still want to perform a powder experiment, they are way too big. For a good powder, you would aim for a homogeneous crystallite size in the single micrometer range. You can achieve this by grinding your sample or squashing it with another microscopic slide or a spatula. Next, you want to mount your samples. For an almost background-free data collection, you can mount quartz glass capillaries or Kapton tubing. Both come in various sizes and can be sealed airtight in order to protect the sample. You can mount them in a standard sample holder or a magnetic mount. For an excellent instruction on how to load quartz glass capillaries, please visit the YouTube channel of the Argonne National Laboratory beamline 11BM. Way quicker is the mounting on a medium-sized single crystal mount, like a nylon loop, a multi-gen mount, or a glass fiber. You apply a little bit of oil to your mount and then dip it into the powder sample. You should not use too much oil, as this leads to an elevated background. The final powder sample should not vastly exceed your beam size, so samples of 100 or 200 microns are fine. If you use the latter technique, it is recommended to deactivate your cryostream completely. Otherwise, your sample might get blown away. You can do so by shutting down your cryostream and also disconnect the dry air inlet for the dry air shield, like in this example for the CryoStream 800. The exact setup of your crystal cooling device might differ. If you use long capillaries, it might be necessary to move the temperature device in order to avoid collisions. Next, we can mount the sample and start the experiment. Therefore, let me switch the screen. You will be able to follow the next steps as they are listed on the left-hand side of the screen. My cursor position is highlighted by a red dot. We start the data collection by opening the online version of CrysAlisᴾEØS. First, we have to mount the sample. Therefore, I press the Start/Stop button and start a new experiment. Then we press Mount. Alternatively, you can press F12 as a shortcut to access the mounting dialog. As you can see, my sample is already mounted nicely. Next, we start the powder diffraction. We start the powder diffraction tool by clicking on the Start/Stop button and select the powder experiment under Other Experiments. Alternatively, you can access the powder experiment dialog by clicking this icon featuring the Debye-Scherrer rings and the powder diffraction pattern on the left-hand side. First, we have to choose the experiment name and folder. Like for a single crystal experiment, CrysAlisᴾEØS will automatically check whether the path is okay. Under the Options button, we find here, we find different options for the subsequent data processing. For now, we remain with the default setup, and we will return to these when we talk about the data processing. Now we choose one goniometer movement for our experiment. The standard phi scan will rotate phi with 1 degree per second during the data collection in order to randomize the sample orientation. The fast phi will rotate phi either at the maximum speed of the goniometer or through the full phi range, which is usually 720 degrees. Gandolfi scans combine a fast phi scan with an omega scan at the same time for even more randomization of the sample orientation. If Gandolfi scan for single crystals is selected, a series of Gandolfi scans at different chi angles is performed for maximum randomization of the sample orientation. Furthermore, it is possible to perform stress and pole figure measurements. For our experiment, we select the fast phi scan. We choose a target resolution range. For our, next we have to choose a detector distance, and here we achieve best results with a large distance beyond the 100 millimeters. Therefore, I key in 120 millimeters as the detector distance. We choose also a target resolution range. For pharmaceutical compounds, we usually aim for a fingerprint region up to 40 degrees in 2 theta. Theta is the detector angle, and we can choose to expand the number of theta positions in order to for better overlap of the frames from different 2 theta angles. In order to save time, we can also limit them to one side of the goniometer. We choose only negative 2 theta positions for our experiment. Then we choose an exposure time. For this experiment, I choose 60 seconds for each frame. Okay. You can observe that the complete experiment time is now calculated to be 3 minutes. We can check the run list by clicking on the Edit Run List button. It opens the very same menu as for any other experiment strategy. Here we can see that 2 frames will be collected. These are two 720 degree phi scans within 60 seconds, each at a different 2 theta angle and a different omega angle. Last but not least, there is an option to perform temperature experiments. You can activate this corresponding checkbox and select your temperature device in this drop-down menu. By clicking on Settings, you can design your temperature experiment. This is the same function as for a single crystal temperature experiment. After each temperature step, the data collection strategy will be performed. For this experiment, we do not use the temperature device. We can now start the experiment by clicking Start with Analysis. This would take a while, therefore I will not start the experiment, and we do the old baking show trick. I have something prepared. Therefore, I now start another instance of CrysAlisᴾEØS. And I load this data set, which I collected today. I now start the powder extraction tool by either selecting it on the drop-down menu next to the 2D analysis tool here, or I click this button on the left-hand side, the power tool. If I do so, a question pops up whether I want to proceed with the automatic pattern extraction. I click OK. And the pattern extraction starts automatically. The powder graph window opens. Here we can see the extracted powder graph and some controls on the bottom of the window. Yeah. We start by adjusting the instrument model. Like in any single crystal experiment, the goniometer and crystal alignment might not be perfect. Therefore, we refine the instrument model for our data. If your data are not suitable for an instrument model refinement, you can also copy the values here on the left-hand side from any other experiment on this instrument. We will adjust the instrument model for the data. Therefore, we need to add some powder rings to the peak list in the middle. We can do so by clicking Add a Ring and select one powder ring in our frame. The ring is now added to the peak list here. And in the middle of the control, we can also perform an automated peak hunt. But before I do that, I will zoom into the frame to make the powder ring, make the overlay better visible. Now I perform a peak hunt. You're asked for a threshold. I put in a threshold of 2 because I have quite low background on the Hypix detector. Also for the average threshold at 2 is all right. And here we see the overlap of the expected and observed powder rings. The expected and observed rings correspond very well. Therefore, I know the instrument model is correct. I now intentionally offset the instrument model to a Y beam center position of 360. You can now observe that the expected and observed powder rings do not correspond as well anymore. I will also increase the delta value in order to get a faster refinement. When I now click Auto Adjust, the instrument model is refined to our data. So the instrument model is now back at its correct values. Alternatively, instead of hunting for rings, you can also add peaks from a known lattice. For instance, if you have a standard in your sample. Next, we are going to check the options. We can choose different output file formats for the powder pattern extraction. We choose all of them here. We can also choose the 2 theta range for the data extraction. And we can choose from a number of corrections for our data. Here I choose the baseline correction. If I want to process, now I reprocess the data and the powder pattern is extracted. Process. The powder pattern is extracted from all frames and is scaled. So we get one powder pattern from the 2 different frames. If we want to process a number of experiments, for like example, after screening or a temperature experiment, we can use the batch mode. Here I can browse for a directory and process experiments in this folder at once. All processed patterns can automatically be copied to one specific folder. There are some tools for the analysis of the powder pattern on the bottom left side. You can zoom into the frame, into the graph by left clicking like this. And you can zoom out again by clicking right. And you can return to the default size by clicking the default size button. You can select a certain 2 theta range by applying 2 theta constraints, like let's say between 16 and 23. So let me go back to the full range. Okay. Furthermore, you can display the expected diffraction pattern of a known lattice. Therefore, I select the lattice information button. And here I can load the CSD known lattice of naproxen. The expected peak position for these letters are now indicated at the bottom of the graph, and they correspond quite well. You can also compare the diffraction pattern to the expected structure factors of a known structure. To do so, I select structure factor, and now I load the literature known structure of naproxen. Also here, the correspondence of the expected and observed data is very good. Now, we can save the plot by clicking on the floppy disk symbol up here. So, and I'll close this window. Oh no. The exported files can be found within the experiment folder. I open the experiment folder by selecting the help menu. Oh. And here it is. And the exported data can be found in the plots red folder, like here. I now resume to my slides. You will not need impeccable data for most cases. For a quick control of your synthesis, a 1-minute data collection with a crude powder will be enough. But sometimes you will need to get good data, and therefore we offer several ways to achieve these. If your diffraction image looks like the one on the right-hand side, it is a symptom of an inhomogeneous sample with larger crystallites, featuring these discrete diffraction spots. These lead to a broadening of the Debye-Scherrer rings and erroneous intensities. This can be treated by grinding the powder or by randomizing the sample orientation during the experiment with Gandolfi scans. If you observe very high background, you should reduce the amount of oil or sample holder in the beam. Or you can switch to a Kapton tube or quartz glass capillary. If your sample is strongly absorbing on a copper source or weakly diffracting on your molybdenum source, it might be worthwhile to change the radiation type. In order to prevent overlap of these powder rings, you can move the detector to a long distance beyond the 10 centimeters, or you can employ the divergence control of your system. The dynamic divergence control is a unique feature of Rigaku single crystal diffractometers and comes in very handy for the collection of powder data. Employing the divergence slits is just as beneficial for powder data collections as it can be for most single crystal measurements. It will improve the resolution of your powder data drastically. Here you can see the improved resolution achieved after employing the slits. The improved resolution leads to the observation of additional peaks marked with red arrows. After the data collection, I want to quickly address the possibilities of data analysis. What I think most people are interested in is the qualitative analysis. Is the sample what it is supposed to be? Most easily and straightforward, you can compare the diffraction pattern to a known substance in CrysAlisᴾEØS as we discussed. For performing a database search for your pattern, we recommend using SmartLab Studio 2. However, if you are working at a university, you might already have a site license for CCDC- or another program. The best renowned databases are the CSD and the PDF databases. If you are interested in qualitative analysis, Jakub Wojciechowski held a talk on this topic during our last user meeting. Among many other talks, this has been published in our X-ray forum. Once you determine the components of your mixture, you can also quantify them by various methods. Here I would like to reference the other webinars of this series that are concerned with this specific applications. Last but not least, it is possible to collect high-quality powder data that are suitable for structure solution and Rietveld refinement. We performed an experiment with this metal organic framework on the right-hand side for a wide 2 theta range and at a long detector distance and with a very low divergence. And we ended up with a data quality very similar to real powder instruments. And with that, I would like to thank you very much for listening. I hope you enjoyed this webinar. Please stay safe and healthy during this time. We welcome your questions and also suggestions for future topics of this webinar series.